Yeah, let's start this up. So tonight we're going to start talking about parametric equations, and then we'll talk about polar equations on Tuesday. So the one thing I did mention that I said once we get to chapter 10, I will have a little bonus credit assignment for you. And this is what I will explain to you right now. So there's 10 points on the line. There's actually 3. I'll do 10 points and I'll do 5 point to 2. We'll do 10 and 5 because class isn't that big. So basically what I want you guys to do is after class tonight or before next Thursday's class is to come up with a cool parametric equation graph on Desmos. So this is one example. It's just the beating heart. This is another couple examples of what people have done in my class. So this is kind of like a little slinky thing that somebody did. Then we had a cool one looking like this. Now these are all parametric equations that they've done. Somebody really went wild and actually drew me. Unfortunately, they didn't win that year. So I'm going to show you a general idea of how to do some of this stuff tonight. And then it's literally just playing around on Desmos to figure out how to do some stuff. So make sure to go back to the beating heart and I'll show you some of the basics of it. So basically when we're looking at, I'm going to show you how to create the parametric equations for the first part. But all this basically does is it's the equation there. And then to get the actual design where it's changing, that's the sliders. So you're just going to put a parameter in there like A, B, any letter you want. And then as that varies, the equation changes. And that's what you actually see the changing of the graph. So on this one, those equations makes the graph get bigger or smaller. So I can actually change this. So because it's basically just adding a little bit to that graph, that's how it's getting bigger and smaller at the same time. And since they're all different, the A, B, and the C, that's how we get the beating heart that looks like it's beating because it's got the different styles in each one of them. So that's pretty much what you have to do. I'll show you guys how to do the actual parametric equations in a little bit when we're starting to talk about what they are and the graph part of it as well. But that's how you get the movement is those sliders in Desmos. To create it, you're going to go to desmos.com. You're going to create the thing, and then you're going to share the graph. So you log in. You can log in with a Google account. It's not that difficult. And then what you do is just click this little button that says Share Graph, and you're just going to send me that the link to the graph in an email. And then on Thursday's class, next Thursday's class, I will share those with everybody, and we will vote on who gave me the best graph. And the top 2 vote getters will win the points. And it'll go on to the lowest test grade that you have. So we'll do 10 points and 5 points. Questions on that? Last week's test, chapter 11, or on Tuesday's test, pretty much everybody did very well on that test. So either you really got it or the review kind of really helped you figure out exactly what you had to do for the questions. Either way, you did very well on it. So, all right, let's go back to my other graph that I had. All right, let's start talking about parametric equations. So a parametric equation is an equation with a parameter in it. So when we're typically talking about a graph, we're typically talking about something with y equals and an x. Now, parameter has actually 2 functions. You have the x function and the y function. And then you have some parameter of t. We typically use t because it's kind of like a time. It's as you're going across. So if you notice on this graph, you'll see those little arrows. That's actually the direction of the graph. So when we're looking at a parametric equation, you actually are going to have direction to your graph as well. So this one, actually, laser pointer. So this one starts down here and goes up, and then goes back, and then goes this way. That parameter is what's giving you that direction. And you also can see how they wrote the equation. It's basically as a point term. So you have your x and your y in the point, and each of those is a function that's going to give you the different values into it. So when you're graphing it, you're actually graphing the x and the y. You're not graphing the t, although the t is what allowed you to find the x and the y values. And we'll see how that does that in a little bit. All right, so I basically just explained that and that. All right, so let's look at one of the examples and see how they come up with it. So you'll notice in this equation right here, we've got x is t squared minus 2t, and y is t plus 1. So that's our parametric equation. And what we're going to do is we're going to pick values for t just like we would pick values for x in like a regular function that we're graphing. So I've got the numbers from -2 to 4. And then we just plug those values in to your x and your y. So when you plug in -2 to the first one, we get 4 plus 4, which is 8. And when over here, we'd get a -1. They just forgot to put the 1 in the graph. So you get -1 there. -1, you get 3 and 0. 0, you got 0 and 1, and so on and so forth. So the points that I'm going to graph, I'm not going to graph this t value at all. I'm just going to graph the x and the y points over here. So when you graph it, we get a graph that looks like this. So that -2 point that I got was 8, -1. -1 was 3, 0. 0 was 0, 1, and so on and so forth all the way up. So you can see how that gave me my curve there. Any questions on how that's done up? And as you can see on this one, they gave you that arrow. So that arrow is giving you your direction. So when we're looking at parametric equations and also polar equations, when we look at those, you'll have a direction to them. And that's actually just as important as the graph.
So we can just use whatever numbers for t, essentially?
Yeah, basically, yeah. So t is just like an x in the typical function where you're just picking the numbers you want to be able to graph it. One of the things you'll notice, actually, that I'll show you, I'll do this one on Desmos real quick. So when you do your equations in Desmos, what you do is you actually write them as the points. X was t squared. So you have t squared minus 2t. And then you had t minus 1. Or t plus 1. And then we close the parenthesis. Now, if you notice, like on this graph, so we went from, on this point, from -2 to 4. So when we're writing it in here, -2 to 4, it's not going to give you the values for t. You have to tell it which range you want to plug it in as. So if you notice, when before they actually had that, it was 0 to 1. It was 0 to 1. And all we saw was that little bit of graph right there. By changing my t values, we start getting the larger graph. But unlike a function, the graph ends where my t values end. So you're not going to see it going on forever in this thing unless you have unless you say your t values go on. So like if you wanted to do -1,000 to 1,000, it's going to look like a typical graph that you're going to have. But that t value is actually, it could be endpoints when you're looking at it as well. So it doesn't necessarily have to keep going unless you're looking at it forever. So that's why if you notice at the end here, there's not arrows or something saying that's going on. It's basically stopping at those points. Does that make sense? All right.
Yes.
Okay. All right. So talked about that. So the other thing we can do is we can also take a parametric equation and change it back into a regular function as well. by just plugging in the value. So on this one, we had x equals t squared minus 2t. And the other equation was t equals y minus 1. So it was actually going to be really easy for me to change the t to y. So actually, it should have been y equals t minus 1, or t minus equals what? Yeah, t equals y minus 1, because it was y equals t plus 1. So it was really easy for me to solve for the t there. And all I do is take that t and I plug it back into the x equation. So this equation, x equals y squared minus 4y plus 3. And if we graph that, x equals y squared minus 4y plus 3. You'll notice it's the exact same graph. So those are two different ways to show the same graph. So we could take a parametric equation and change it into a function in some ways. It's not always going to be true. It just depends on how complex the function is and if we could actually solve it for the x or the y. Some equations that you're going to see in a little bit, there's just no way to do that. So, but this one there was. So this is what I was talking about a bit ago. We can look at it. So we can look at t as going from infinity to infinite, negative infinity to positive infinity, or we can look at it as going from specific points. Like, so this one, they restricted from 0 to 4, and you can start seeing how that curve goes. So we can actually restrict it. So you're only looking at specific values of it. We talked about the arrow. The initial point when you're plugging it in is that initial value. So when we're plugging in the A, and then we have our terminal point, and when we're plugging in the B. So you can have, if we're looking at a finite things, we have initial points and terminal points as well. All right, so let's look at the next one here. So we've got x equals cosine of t and y equals sine of t. Since we're looking at it in terms of sine and cosine, we're going to use 0 to 2 pi for this one instead of specific numbers. This way we can use that, make the t as radians. It'll make our lives a little bit easier when we're graphing them out. Now, so if we plotted these points, so if we're going to go over here, let's do this. Cosine. So we have cosine t and then sine. Oh, turn those off. Then we're going from 0 to 2 pi. And we get a circle. So as you can see here, when we graph sine t and cosine t, or we get our circle, and we're going from 0 to 2 pi. If I go any higher than that, it's not going to change anything because it's just going to keep repeating, going over and over again. But I can go lower. So like if I just did it from 0 to pi, I get a semicircle. So this is one of those functions that we can't typically graph on a normal curve because we have the x squared and y squared, so it's not a function. And parametrics makes it quite easy to be able to do that in graph. We do have our equation for a circle. It's x squared plus y squared equals 1. And if we look at this, if x is cosine of t and y is sine of t, we have cosine squared t plus sine squared t equals 1. And that right there is just one of the Pythagorean identities. The sine squared t plus cosine squared t equals 0 or equals 1. So we do have that same situation there. And then if we look at it, you can see when we're looking at our unit circle, which you probably remember from back when you did the in pre-calculus, we had our cosine was the x values and sine was the y values. So you can see how that actually then creates that unit circle right there. So, and we're going from 0 to 2 pi, so that's where you get the whole circle. Notice there are arrows on these as well, because it's showing the direction that we're going, because it is a parameter. All right. So one of the things that we can do when we're looking at graphing calculators So graphing devices actually makes our lives a little bit simpler to do these, and that's where we're looking at Desmos. So Desmos actually allows you to do a lot of graphs. So we can actually graph this equation right here, the x equals y to the fourth minus 3y squared in Desmos. So in Desmos, we can graph this. This is not something that all calculators can graph. Most of your earlier TI calculators could not graph this because they wanted everything in terms of y. So one of the things that you wanted to do is if you wanted to graph some of these equations, you would actually have to change them to a parametric equation. So we actually can make it a very simple parametric equation by just changing the x to the t and then saying y equals t. So we can actually do it this way. So all we're changing is y to t. And in your graphing calculator would actually have allowed you to graph this. I put a y there. Now, the same thing you'll notice. See how I'm just going from 0 to 1, and I've just got that little bit of the curve right there, where that first one graphed the whole thing. So if I wanted to see the whole graph, I have to make it a little bit bigger. So, and that gives you the exact same graph. So you can make basically any equation that you have into a parametric equation by just changing the letters to t and setting that whatever letter you have. So either the y equals t or the x equals t, depending on which the equation was solved for, and graph it as a parametric. This was actually one of the tricks that you had to do on the TI graphing calculators to be able to graph equations that were not functions. Now, here's some other little cool graphs. So like this one we could easily do. But when you start to get a little more complicated graphs, like here, let's look at this one. So this is a parametric equation. Notice how there is no way you'd ever be able to graph this out by hand, nor is there a way that you'd be able to graph this out with just a simple equation. So this one is t plus 5t, and then y is t plus sine 6t. And you can see how it's this cool little graph there. So this is also a parametric equation. So you can start seeing how if you start playing, especially with the trig functions, you can start to get these really cool, like almost like graffiti type graphs out of it. Here's another one. This is if we have to zoom in for this one. This is a box. And actually, here, I'll do a little cool thing. So change that to A and change that to B. And let's change. And we're going to play these now. So this is the same equation that we just graphed, except what I'm doing is I'm actually varying the x and the y, or the equations that are in there. So you can start to see how it actually changes it. And this is one little play where you can do some animations. The only thing I changed was instead of putting a 9 and a 10 there, like was in the equation, I just changed them to values that actually change. And hopefully I'm not giving anybody seizures while doing this. So the original problem was 9 and 10, and you can see the original graph. So while you're varying it, you can get some cool little shapes with it. That's one of the things that when you're trying to design your cool graph that you're going to get everybody to vote for, animation definitely makes it a little bit nicer. All right, let's look at one more. So this is another cool little graph. So in this one, we're taking and we're actually adding two cosine functions together. And in the other one, we're adding two sine functions. So we get that cool graph out of there. So you can start to see how the graphing calculator really helps you design things. And you can start to see some cool little shapes and graphs and stuff that can come out of parametric equations. That's why I always like parametric and polar equations, because you could actually draw some cool things out in graph form. If you were ever in high school, you ever took a graphic calculator, drew like the petals, the flowers, those are actually polar equations, and we'll look at those on Tuesday. You actually get the nice little flower graphs out of it. All right, any questions with the parametric equations before we go into all the hard stuff of how to do calculus on it? All right. Oh, shoot, we got one more thing. Sorry, I forgot about the cycloid. So the cycloid is actually a very important graph. The cycloid is actually what would happen if I took a circle and I rolled it with a point on it. So you can see that point right there. And if I rolled, as I roll that circle, that point moves. And as it rolls over a flat surface, it creates what's known as a cycloid. The cycloid actually is used in a lot of different things. So knowing what that graph looks like and how it's created is very important. So you can actually see how it's done. It's the same thing we were doing before with the graph. And your equations for it are the r theta minus sine theta and y equals r1 minus sine theta. R is actually what's, in this case, the reason we use r instead of t is r is the radius of the original circle. So the bigger the r, so that's a value that you're going to have. That's not going to change when you're doing it. So that's that radius value. And the theta is actually the parameter in this case. So unlike the ones we were doing before with t, these are thetas. Hold on one second. I got to shut this door. Sorry about that. My second dog is coming home and the other dog's going crazy. John Bernoulli looked at it as this was the cycloid and actually was looking at it in terms of the curves. And he specifically, one of the things he was looking at was actually the curve of your eye. The actual lens and stuff is actually a cycloid. All right. We kind of already looked at the families of them. This is where we actually have those values that change. So as the A changes, the graph's going to actually change. We kind of looked at that with those the sliders and whatnot. Actually, I have one of those done, so I can show you the specific one. So this is the family of parametric curves. So the curve stays the same, but as the A changes, you can start to see the graph change. And when A is 0, it's actually a circle because it's just cosine and sine. But as it gets further and further, you can start to see the graph changes. And the same thing on the negative side. So these are just families because there's actually a value that changes as you go to create the different values of graphs. All right, now onto the calculus. All right. So when we're looking at the calculus when dealing with parametric equations, we have the same situation. We're still going to be looking for the same times. We're going to be looking for tangents. We're going to be looking for areas. We're going to be looking for arc lengths, and we're going to be looking for surface area. So those same values are still going to come out to play. The difference is we don't have an X and a Y value. We have that T in there. So we have to look at it a little differently than we did before. So my equation, so if we look at dy over dx, that would be my derivative in terms of x. So if we have a dy over dt and a dx over dt, when we're doing the derivatives, we're actually going to have, so my derivative dy dx is the derivative of y over t divided by the derivative of x over t. So all you're doing is dividing them, basically having deriving it in terms of t instead of in terms of the x or the y. So that right there is my first derivative. We're also going to look at the second derivative. So the second derivative, we're going to take the derivative of my first derivative and we divide it by dxdt, the derivative of just the x term. So it's not just taking the derivative of the first derivative like you would in terms of the regular y and x equations. We actually have to divide it by the original derivative of the x term as well. So we do have that piece there as well. So that right there is your second derivative equation, the d dt over dy dx divided by dx dt. Now let's actually use it. In 1 second, my computer, the one that I was going to use to do this, shut down. So. All right. So we have our parametric equation that we're going to look at. In this case, it is x equals t squared and y equals t to the third minus 3t. So let's actually look at this on Desmos so you can actually see what the graph looks like first. Squared. All right, so that's what my equation, that's what my function is going to look like. Now, we want to find, the first thing that I want to find is show that C has two tangent points at 3, 0. So if we look right here, if you look at 3, 0, notice how the graph goes through it twice. So that means I'm going to have two tangent values there. I'm going to have the tangent value going one direction, and then I'm going to have the tangent value going the other direction, because there's actually two graphs there. That's not just one point. So that's the first thing we want to find out, is that we want to show that there's two tangent points at t equals 0, or at the x value of 3, 0. So the first thing we want to figure out is I need to figure out what the value of t is at that point. Okay, so I have my x value and I have my y value. So if we look at, so my first thing is my point is at 3, 0. So the values when this works, we're going to look at the y value because it's the 0 point, which makes my life a little bit easier. So y is 0. I have t to the 3 minus 3t. So if I factor out a t, I get t squared minus 3. So in this case, I get t could equal 0, or I have t squared minus 3 equals 0. So t squared equals 3. So t equals the square root of 3, plus or minus. So I have 3 different values that will work at that point. But it's also got to work for the x value as well. So if I look at the x one now, so I'm going to plug in 3 there and t squared. And the only one that works for this one is plus or minus square root of 3. So I've now shown that there's 2 t values that will work at when my point is 3, 0. So everybody understand where that came from?
Yeah, you just plugged it back in to solve for.
Yeah.
Yeah.
And it has to, the big key is it has to work in both of them. It can't just work for one. Because if you just did it on the one, you'd say, oh, I have 3 points out there. But the 0 doesn't work in the other one. So I know my t works at the square root of 3 plus or minus the square root of 3. So next thing we have to do is we have to find my derivative of my function or of my parametric equation. So I've got the x equals t squared and y equals minus 3t. All right, so my derivative, so my dy dx is dy dt over dx dt.
We can't see what you're writing right now.
Oh, I switched screens. There we go. All right, so my derivative is dy dx, which is dy dt over dx dt. So we now basically have to do the derivative of both of them. So the derivative of the y is 3t minus 3, or 3t squared minus 3. And the derivative of the x is 2t. So now that I've got that, I can simplify this down a little bit. And it ends up being 3 over 2, t minus 1 over t. So that is my derivative. Okay. Now, what's the derivative give us?
Would it be the slope?
Yes, derivatives are slope. So that is going to be the slope of my my parametric equation at any given point. But now I was specifically looking at looking at a very specific value. I was looking at my point was 3, 0, and my t value was plus or minus the square root of 3. So we now have to plug that back into the function. We have to plug my t value into my derivative to find the slope at that point. So when I do the value in there, so I have 3 over 2 plus or minus the square root of 3 minus 1 over plus or minus the square root of 3. So if we simplify this down, all right, we're going to actually just deal with we'll just deal with the positive version first, and we'll do the negative version. They actually come out to be the exact same. So I'm going to simplify this up there. So I'm going to, rationalize this denominator. So I get square root of 3 minus square root of 3 over 3. So that would be 3. So I get 3 square root of 3 minus square root of 3 all over 3. So I get 2 square root of 3 over 3, and that's times the 3 over 2 in front. So this comes out to be just the square root of 3. And if we did the -1, it actually comes out to be the same thing. This is not always the case. Your slope is not always t. So don't think about it that way. So my slope is plus or minus the square root of 3. So now my two equations, when I write my equations out, we're going to use the point slope form. So we're going to use the y minus y1 equals m x minus x1. So my equations for my slope is y minus y1 will be 0 equals square root of 3, x minus 3, and y equals negative square root of 3, x minus 3. So those are the two tangent lines. At that point. Does that make sense? And if we go back to our graph, if we look, if I was to graph that equation, so y equals 3 x minus 3. And then the same thing here. It's minus. So we can start seeing that it goes right through that point. And if we zoom in, it's a little lighter. We zoom in, you can actually start seeing that those are tangent lines to that equation. Okay. All right. The next thing it wants us to find is it wants us to find the points where C has a horizontal or vertical tangent. So if we look here, if we turn those off for a second, it looks like I have a horizontal tangent down the bottom here. Looks like I have a horizontal tangent up top here. And it looks like I have a vertical tangent over here. But we have to figure out the t values that are going to give us those. So how would I figure out a horizontal tangent?
You could do like y equals 2 or -2, right?
Well, you got to remember though, we don't. So I've shown you the graph, but we have to be able to do it without looking at the graph to determine it. So
Yeah.
what do we have that we can actually then use to figure out a horizontal tangent? What do we know about a horizontal tangent that I can use? Horizontal tangents, what's the slope of a horizontal tangent?
The derivative.
Right, so the slope of a horizontal tangent is always what? What's the value? Horizontal line, what's my slope of a horizontal line?
0.
Right. So all we're going to do is we're going to set our derivative to 0. Now, if you remember, my derivative was, what was it? I have to flip back. Give me 1 second. So it's 3t squared minus 3 over 2t. And I want this to equal 0. So the only value that I need to look at, so when I'm looking at my derivative equaling 0, I'm just looking at the top equaling 0. So it's just that dy dt. So I just need to set 3t squared minus 3 equals 0. So t equals plus or minus 1. So we've got the two t values that are going to give me my horizontal tangents. But now I got to figure out my points for those. So we've got to plug back in that plus or minus 1 to my original equations. So remember, x was, so x equals t squared and y equals t to the third minus 3t. So when we plug in 1, I get 1 squared is 1, 1 to the third is 1 minus 3, so that's negative 2. And when I plug in negative 1, I get 1, negative 1, so that gives me a positive 2. So those are my two horizontal tangents. And if we look back at the graph, that makes sense. 1, negative 2, and 1, 2. But that's how we'd find it using calculus to determine those values instead of just looking at a graph and trying to determine it. Does that part make sense?
Yes.
Yeah.
All right. Now, I got to find a vertical tangent. So what do we know about a vertical tangent?
The slope is undefined.
Right, my slope is undefined. So that means if I'm looking at it in terms of a fraction, what does that mean in terms of a fraction?
There's a 0 on the bottom.
Correct. So all I'm going to do is set my denominator equal to 0. So 2t equals 0. So that means t equals 0. And now we're going to do the exact same thing. I'm going to plug that back into my 2 points. So x was t squared and y was t to the third minus 3t. So x equals 0 and y equals 0. So my vertical tangent is at 0, 0. And if we look back at the graph, that also makes sense. So we now have my horizontal tangents at y equals negative 2 and y equals 2, and my vertical tangent at x equals 0. And my two tangents at the point there. All right. So we've determined all the tangent lines. Yes.
Could you just flip back to the board real quick?
No problem. So now that we've determined all of our tangents, the next thing we want to look at is we want to figure out the where it's concave upwards and where it's concave downwards. So to figure out concavity, we need to look at our second derivative. I know I'm not writing. I know I'm not writing on the screen. I'll flip over 1 second. I just want to write the equation first. All right, so my second derivative, d squared y over dx squared, is d over dt times the basically derivative of dy dx. So that's the derivative of what we just found, divided by the derivative of x. So if we look at this, my original function, the dy dx was 3 over 2, 1 plus 1 over t. Oh, minus, not plus. Minus. So that was my original function. And the dx dt was 2t. So now I need to find the derivative of the 3/2 times 1 minus 1 over t. And this derivative, we do that, comes out to be 3/2, 1 minus 1 over t squared. And then divided by my derivative of the other function, which was 2t. So if we simplify all that down, I get 3t squared plus 1 over 4t to the third. Does everybody understand how I found the derivative of this?
So you took the derivative of the top one, but why isn't 2t become just 2?
Because you're not doing the second derivative of that. That's just the dx dt.
Okay.
So it's still the derivative of the original function. So that's really the key piece of this, is this down here, this part right down here. That's still the first derivative. That's the exact same thing as what we had in the original first derivative function. All right. To figure out concavity, we need to know where it's concave up and concave down. So it's concave up when it's greater than 0, and it's concave down when it's less than 0.
Where do we get that assumption from?
Back from when you did Calc 1.
Okay.
That's the original rules for that. It's always concave up. So this, once you find the second derivative, it's concave up when it's greater than 0, and it's concave down when it's less than 0. So basically, it's concave up when it's positive, and it's concave down when it's negative.
Okay.
All right. So basically, what we want to figure out is where this is going to be, where it switches. So if we say where this is greater than 0, so we get 3t squared plus 1 is greater than 0. So what we end up getting is t is greater than the square root of -1, which can't happen. So since you can't actually find that part there, it always ends up being, it always ends up working out when t is greater than 0 or less than 0 in this problem. So if we look at our graph, you can see that here. When t is greater than 0, we have our concave up, and then we have our concave down there. Sometimes you can calculate it out, sometimes you can't. It's just the way it works out in this one. It didn't work out because the bottom can also be negative. And I didn't take that into account today. So that's how you figure out your concavity up and down. And the last thing I wanted you to do is sketch it, which we did on the graph. Questions on that part? Finding your tangent lines and whatnot. Right. Area. So if we look at area under a curve, my function is, it's the integral from a to b of f of x dx. F of x is really what? F of x is really your y. F of x is just another way to write y. And d of x is the derivative of x. So if we're thinking about it in terms of a parametric equation, we have my y and we have my dx. The y is whatever the y term was. So for this problem, it's the g of t. The dx is the derivative of my x term. So the derivative of f of t. So when we're doing the integral to find the area, it's the y term times the derivative of the x term, dt. Does that make sense? So you can write it either way. It just depends on how you're going to remember it. I personally like the y dx. But sometimes when you do y dx, you don't remember that dx is actually the derivative of x. So you forget that part, and then you're all confused when you have a t in your derivative and you're trying to derive by x. So this way, with the g of t and the f prime of t, works out a little bit better sometimes for people, because it forces them to recognize that they have to actually do the derivative of the x term. Questions with that one, or we go with that before we actually try to use it? All right. Let's use it on the cycloid. So the cycloid was x equals r theta minus sine, or r times theta minus sine theta, and then y equals r times 1 minus sine theta. If we're using this in terms of the r, we're going to actually do this integral with r. R is a constant, so we're not going to think about r as a variable that we're deriving around. We're just going to pull that out, just like it'd be a constant or a number. So the first thing we have to do is my y is just r1 minus cosine theta. Now my x, I have to do the derivative of. So I'm looking for the derivative of theta minus sine theta. So the derivative of theta minus sine theta is 1 minus cosine theta. Because the derivative of theta would be 1, and the derivative of sine theta is cosine theta. So that's also r1 minus cosine theta. And then I have the d theta at the end. So the r's are going to come out. I get the r squared out. And then I have 1 minus cosine theta squared. Which we FOIL out, and I get 1 minus 2 cosine theta plus cosine squared theta. Are we good to that point?
Where does the r go at the very beginning? It says 2 pi r. At the top of the interval. Yeah.
Because it was based on the radius at that point. And notice how the r's are then actually used inside of the function at that. So the r's are there.
Okay.
And actually, I think that might be an error, but because they were using the substitution rule to substitute everything back in, so they actually plugged in the 0 and the 2 pi into the problem. You're never going to actually write it like this. You're always going to end up writing it like this at the end. So I wouldn't overly worry about that R value there. The big piece is don't forget that the R's are very like constant, so you can just pull it out. Because if you left the R in it, it's going to be messy to try to do your integral out. All right, when we're looking at the integral, we don't have an integral of cosine squared. So we have to change that. So you have to remember your half angle formulas. So we have 1 minus 2 cosine theta plus 1/2, 1 plus cosine 2 theta. Now that we've got rid of everything and I can actually do the integral of it, so we do the integral of 1. We do the integral of 2 cosine theta. So the 1 theta is going to be 1 theta. 2 sine theta becomes negative 2, or negative 2 cosine theta becomes negative 2 sine theta. And then we have the 1/2 times 1, which is 1/2, which is where that 3/2 comes in, because it's that 1 plus that 1/2. That's where the 3/2 theta comes from. And then cosine 2 theta becomes 1/4 sine 2 theta. Because you have to do that U substitution on the 2 theta, which gives you another 1/2. 1/2 times 1/2 is 1/4. Questions on that? It should be pretty straightforward. Once we've got our integral done, we can plug in our 0 and 2 pi. 0 is going to cancel everything out because sines are always, when you do sine of theta or 0, you get 0. So the 2 pi is the only one that really matters. But sine of 2 pi is also going to be 0. So that it cancels out those as well. So the only thing that's left is that first one, 3 over 2 pi. So it's 3 over 2 times 2 pi, which gives you 3 pi r squared. So the arc length or the area under the curve, this area, sorry, the area under the curve for a cycloid is 3 pi r squared. So whatever the radius is, square it, multiply by 3 pi. That's going to give you that area under that curve. Any questions on that one? All right, 2 more formulas. Next thing, we're going to look at arc length. If you remember back when we did the arc length formulas back in, I think it was chapter 6. So we had the arc length was 1 plus the derivative of the function squared. So in this function, we're going to have the dy dx squared. So we're going to have to break that up. So the dy dx is dy dt over dx dt. So we split that one up and we end up getting the function as, or solving it out, simplifying it, doing the common denominators and all that other stuff. We get dx dt squared plus dy dt squared. So it's in essence the square root of x squared plus y squared, which if you remember back to the original distance function back when you did it in high school, it was the difference of x's squared plus the difference of y squared. And then you take the whole square root of it. So it kind of makes sense that that's what would be the function here. So that's the function for arc length. This works for any arc. So as you can see here, this is a really crazy arc. Even though it goes up and down, left and right, and all this other stuff, that arc length formula will find the length of that function. Because it's doing it in terms of t and not in terms of the x's and the y's, it doesn't matter where it is or if it goes back on itself. It's doing it in terms of the t, so it knows that it's going to do that part there. This is all literally coming up to tell you the equation. So as you can see here, this is just another way to write it. The derivative of t squared, or the derivative of x squared plus the derivative of y squared. All right, so there's my equation. Let's use it. All right, so we're going to do it in terms of a cycloid. So we have my same cycloid function. Now we're going to figure out the arc length. We're going to figure out how long one of those curves actually are. So I have the dx d theta. So I have the derivative of that one is 1 minus cosine theta. And the derivative of the y is just sine theta, because the 1 disappears and the negative cosine theta becomes positive sine theta. I would do that first before you plugged it into the function. Just makes your life a little bit simpler and breaking it all down. And also, when you're dealing with sines and cosines, make sure you go the right direction. It's really easy to mix those up when you're doing the derivatives and the integration, because they're basically the same. You just keep flipping, and you easily mess up your signs. All right, so we're plugging those values in. So I've got r squared 1 minus cosine squared plus r squared sine squared theta. I can factor out the r squared, break down the FOIL out the 1 minus cosine theta, and I get 1 minus 2 cosine theta, cosine squared theta, sine squared theta. Now that cosine squared theta plus sine squared theta is 1. So that piece right there disappears. And I can pull out the r squared because it's a constant. So I can pull it all the way out in front, and it's just r because I did the square root of r squared. So I'm left with inside, I have 2 times 1 minus cosine theta. And then I have to do the integral of that. So we have to do, we have to change that to sine squared x. So sine squared x is 1/2 1 minus cosine 2x. So if I'm going to say theta is 2x, that's going to give me 1 minus cosine theta is 2 sine theta, or 2 sine squared theta over 2. So once I plug that into the function, I get 4 sine theta, or sine squared theta over 2, which I can now do the square root of. So I have 2 sine theta over 2. And since my values are, I have the 0 to 2 pi, it's actually only going to be 0 to pi because I'm cutting it in half. Sine is always positive between 0 and pi. So therefore, I don't need to worry about my absolute value. Questions on that? We actually have not done the integral yet. We've just simplified down the square root. Now I got to find the integral of it. So the integral of sine is negative cosine, but I have to do the quick use substitution. So I get negative 2 cosine theta over 2. And the 2r came from, there was a 2 there, so I pulled that 2 out. That's where that 2r came from, the 2 that was in front of that sign. So if we plug in 0 and 2 pi, so for cosine, 0 and 2 pi are both 1. So when I plug in 2 pi, I get, or cosine of pi is actually negative 1. So I get negative 1 times 2, or negative 2, which is 2. And when I plug in 0, I get positive 1, but it's minus that, so it's minus a negative 2, which is positive 2. So I get 8r is my arc length. So it's 8 times whatever the radius is, would be the arc length for the cycloid. Does the process make sense for finding arc lengths? It really ends up being, I mean, just how easy the actual integration is once you find thing out. The formula is actually pretty straightforward. All right, last one. Surface area. So the surface area formula is just like we did surface area before. It's just 2 pi times y times whatever the arc length was. So we take our arc length formula and we're just going to do 2 pi y times it. The thing with this one though is remember, y is not y. Y is whatever your function for y was. So we do need to make sure we plug that in. And the square root part is exactly the same thing as what we just did with the arc length. So make sure we have that equation down. That's my surface area function. All right, so let's find the surface area of a sphere. So if you remember back in geometry class, the surface area for a sphere is 4 pi r squared. So let's prove that that is correct. We know our sphere could be made by just doing a semicircle, just rotating it. So remember my circle is r cosine theta, or t in this case, r sine t. Since I only want a semicircle, I'm just doing from 0 to pi. I'm not going to do 0 to 2 pi. So that's going to give me my semicircle, and then I'm going to rotate it around the x-axis. So my function, or my integral, is 2 pi times y, which is r sine t, and then square root the derivative of x, which is negative r sine t, and the derivative of y, which is r cosine t squared. Any questions on what we just did there? All right. So now we're going to go through and simplify this out. I can pull out the 2 pi, so I don't have to worry about that part. I have an r squared inside here, so that's just going to become r. The sine squared theta, or t, plus cosine squared t, that's just 1. So in essence, it's r sine t times r. The r's can come out because that's just a constant. So now in front I have 2 pi r squared. And all that's left inside is sine t, of which I'm going to do negative, take the integral of that, and it's negative cosine t. Plugging in 0 and pi, when I plug in 0 to that, I get negative 1. And when I plug in pi to that, I get positive 1, so I get 1 plus 1, which is 2, and I get the 4 pi r squared. So we have proven that the surface area of a sphere is 4 pi r squared. And that's it.